Alright guys, so today we're going to look at how the derivative helps us determine intervals where the function is increasing or decreasing. But first, let's talk about what does it mean for a function to be increasing or decreasing. So if you have a function whose graph is something like this, so some parabola, you would note that here in this relative maximum, you can partition the real line into two intervals. On this interval, I think we all agree that the function seems to be increasing. And on this interval, we agree that this function is decreasing. So mathematically, how do we define that? Well, if you have an x here and say a y here, you have that f of x is less than y, f of x is less than f of y. So that's going to be how we define the function being increasing. So let's do here f be defined on an interval and this is what I was struggling with the space, but we'll move over here. We say that f is increasing on the interval I, if and only if f of x is less than f of y, less or equal, whenever x is lesser or equal to y. So, in other words, f preserves the inequality, preserves order. And then for decreasing, you write the exact same. However, in that situation, you have that if you get your x less than y, so let's grab an x here and a y here. Now f of x, which is the y coordinate here, I'm going to write it on this side just because it's going to get too messy. Otherwise, f of x is now greater than f of y. So x is less than y, and f of y is less than f of x. In other words, the function is decreasing if, and I should call it g or something, but now I already wrote it with an f, if and only if the order is reversed. So that's going to be whenever the function is decreasing, the order will be reversed. So that's just to know how it would be defined mathematically. So now the theorem we need for this whole section is the following. If f is continuous on the closed interval a to b and differentiable on the open interval a to b, then if f is, the derivative rather, is greater than 0 on AB, f is increasing on I. Well, I called it the closed interval from A to B. Sorry about that. Now for decreasing, if the derivative happens to be negative, the rest goes the same, then the function f is decreasing. And if f happens to be equal to 0, identically 0 on the whole interval, open interval, then f is constant. So using this bit of information, we will be able then to find intervals where the function is increasing and decreasing. But why do we care about that? Why are we even interested? Well, because you notice there's something interesting, something good that happens whenever the function passes from increasing to decreasing. You have a relative maximum there. And when the function goes from decreasing to increasing, so if we were to continue like this, then when you go from decreasing to increasing, your function gives you a relative minimum. So then we're going to put all this together to do what is called, or to write what is called the first derivative test to classify relative extrema. But we'll start just looking at the intervals where the functions are increasing and decreasing, because that's going to be useful for us to classify extrema later on. So let's go ahead and do that. Let's do a few examples. Okay guys, so I wrote the example here. So find the open intervals on which the functions are increasing or decreasing. We're going to do several, so I'm going to just keep adding functions as we go. So let's start with this one. It's a parabola that opens down. So let's try to figure out when is it going to be increasing or decreasing. So it's going to be very similar to the example I gave you, except now we're putting numbers to it. So let's first find the critical numbers. So our first step is to find critical numbers. So we're going to set the derivative equal to 0. In this case, just 0 because it's a polynomial. So derivative, negative 2x minus 4. So we set it equal to 0. Add 4 on both sides. Divide by negative 2. And you get negative 2 as your critical number. So what's going to happen is you're going to have two intervals. So you draw your real line. Negative 2, you place it somewhere here. And so you have this partitions your line into two intervals. One from negative infinity all the way to negative 2. And the other interval from negative 2 to positive infinity. So these are going to be my intervals. What I'm going to do is I want to know what the sign of the derivative is on each one of these intervals. Now, since I know the only possible 0 of this derivative, or this polynomial, in this case that line, is x equals negative 2, I know to one side of the 0 I get one sign, and to the other side of the 0 I get another sign. So the only place where the function or the derivative could change signs would be at negative 2. So what I'm going to do is I'm going to pick two numbers, one to the left of negative 2, one to the right. So here 0 is perhaps more convenient. And I'm going to find the sign. I'm going to call this a test value, if you will. And I'm going to look for the sign of the derivative at that point. So let's take a look. Let's evaluate it here. Perhaps it's better. So at x equals to negative 3, my derivative is going to be equal to negative 2 times negative 3 is going to be positive 6 minus 4 is positive 2. I really do not care about what number we get. All I care about is about the sign. I get a positive sign there. So at x equals 0, the derivative at 0, you can see you get negative 2 times 0, 0, minus 4 is going to be negative 4. As I said before, we don't care about the value, we care about the sign. So what I get then, a conclusion, I could have given myself more room to write my titles better, but oh well. Increasing to decreasing. So what happens is the function is increasing on the interval negative infinity to negative 2 and decreasing on negative 2 to positive infinity. So right there we get our solution. But if you look at it graphically, what it happens is this graph, I have the intercepts here so we don't have to guess them. So negative 5, to positive 1, and at negative 2, which is right in between those two numbers, let's put it there, a little further to the left would have been better, but the graph then it looks something like this. It's a parabola that opens down. It has a vertex at negative 2, comma f of negative 2, whatever that number gives us. And it is going to be increasing from negative infinity to negative 2. And it's going to be decreasing from negative 2 to positive infinity, as we stated. So sometimes it would be convenient for you to go to a graphing calculator, or say Desmos or any other software that would allow you to graph the function and verify a result. Once you get your result, go look at the graph and make sure that it matches with what you computed. Don't do it all the way around, because then it's clear that you're not going to have all the steps, and it's going to be pretty obvious what you did. So do it in the right order. Finish your example and verify your results with a graphing calculator. Let's do another one. All right, so let's take a look at this one. Now we have a cubic function, but the strategy is still the same. Take the derivative, find critical numbers. And whenever you have a polynomial, remember that you will have only to check for the derivative being 0. We don't have to check for the derivative when it's undefined, because polynomials are always going to be defined. So no problem there. So let's take our derivative here. So I drop the 3, subtract 1, drop the 2, subtract 1, as we've been doing. And I'm going to set that equal to 0. So let's do one thing. Now let me do it in steps. My bad. Me trying to skip steps, not a good thing. But, so now I'm going to multiply times negative, because I need to factor this if possible. If not, I'm going to go ahead and do a quadratic formula. So whenever you have a quadratic equation, try to factor. If you get stuck, don't stay there stuck for too long. There's a quadratic formula for you to solve it, so just don't stay stuck for too long. So let's multiply this times negative 1, because whenever I factor, I prefer to have a positive leading coefficient. Maybe that's just me, but I think it would be convenient. So here you could do it with the AC method, or you could just look at factors and trial and error get them. I think we're going to get them trial and error, just because we have plus minus 1 here as our possible factors, and I have a negative 2, so maybe if I do a negative 1 here and a positive 1 here, when I FOIL it out, I get negative 3x plus x, which gives me negative 2x as needed. So right there we have our factorization, and now we get two possible critical numbers. Let me write them out. So for the first one, I get x minus 1 equals 0. From where I get x equals to 1. That's going to be one critical number. And for the second one, or the one on the left, 3x plus 1 equals 0. From where I get, well, subtract 1 on both sides. 3x equals negative 1. And I divide by 3, I get negative 1/3. So let's go ahead and put our numbers here. Negative 1/3 and 1. And that's going to give me 3 intervals. From negative infinity to negative 1/3. It's going to be a little bit tight, from negative 1/3 to 1. And then from 1 to infinity. So those are my 3 intervals. And I'm going to get test values. So test values in each one of these intervals. From here to the left, I probably can pick negative 1. That would be perfectly fine. Between these two guys, I can pick a 0. And to the right of 1, I'm going to pick a 2. All I'm trying to do is grab a number that is inside of the interval. Which number I pick, it doesn't matter. But I tend to favor those that are going to be easy to evaluate later on. Excuse me. So let's go ahead and evaluate the sign of the derivative. By the way, remember, you're evaluating the derivative, not the function. That happens as well. So this evaluation happens to be easier on this form. Why? Because, well, if we evaluate, let me do a little, I could fit it here, I guess. So at x equals to negative 1, my first test value, when you plug this in here, you're going to have 3 times negative 1 plus 1 times negative 1 minus 1. So why do I say it's easier to evaluate here? Well, because you just have to add smaller numbers. So 3 times negative 1 is going negative 3, plus 1 is negative 2, so negative. Negative 2 here, negative times negative is positive. So when you have that, you put your positive here. At x equals to 0, you evaluate it here again, you get 3 times 0 plus 1, and then 0 minus 1. And you're going to get positive, so positive 1, negative 1, positive times negative, negative. And we evaluate at x equals to 2. And at x equals to 2, I'm going to have 3 times 2 plus 1 times 2 minus 1. This is going to be 6 plus 1, 7, positive. 2 minus 1, 1, positive. Positive times positive, positive. So you see, when you evaluate it here, the numbers are smaller than if you were to plug it here. Then you get it becomes a lot more difficult. It's a lot easier once you have factored it to plug it into the factor expression. So the conclusion is going to be that on this interval, it's going to be increasing the function. Here it's going to be decreasing. I just write that because it's not going to fit it here, and then increasing here. So we have that the function will be increasing. I'm going to summarize my conclusion because I took some space here, but I'm going to have that the function will be increasing on. You're going to grab the first interval, so from negative infinity to negative 1/3. And then you're going to say, I also need this interval, so I'm going to do a union 1 to infinity. And for the decreasing, the function will be decreasing on the open interval negative 1/3 to 1. Now, here's a cautionary tale. You notice how the signs are going to appear plus, minus, plus. And then it'll happen very often where the signs will alternate. But that is just related to the multiplicity when you factor your zeros. So when the zeros of multiplicity, odd multiplicity, you're going to have that the sign will change. Sorry about that. But if you had an even multiplicity, let's say you would have a 2, then the signs will not change when you go through that 0. Because remember, when you have a graph of a function, when you go through a 0 of multiplicity that is even, then that graph bounces off the axis and doesn't cross. So the moral of the story is it will not always alternate. It will very often alternate, but it will not always alternate. So be very careful and evaluate it, even though it seems tempting that you will just compute one and then just alternate them out. It will cause trouble because you will find one where you have a multiplicity 2 and it wouldn't alternate, and once you cross through that one, if you alternate when you shouldn't, then everything else to the right will be wrong. So you'll get the wrong answer and you will be upset because this took only a minute to do, and for saving that minute, you could end up with the wrong answer.